Welcome, guys. Yeah. So this is the fifth video of the word representation, and I think should be for the theory part should be the final one. So yeah, I think so. In the previous video, we already proved this one, which is the so-called row orthogonality, and also prove the grand Schur orthogonality. If you see this video, basically it's just from Schur's lemma. So the rest is that to proving this is so-called Cardan orthogonality. So this one is a much difficult one, and which connected use the conjugate class, and we need to define our so-called class function. Okay, so if you don't know you need enough group theory knowledge, you can go to my previous list about group theory. And I think maybe you only need this. I think you only need the number 3 and number 4. From 1 to 4 is already enough. Okay, so what I trying to prove previous, this is our goal, right? The goal, we have two goals. Okay, so the first goal is that we need to prove that the number of the irreducible representation for the finite group is the same as the number of conjugate class, or somehow people like to call it conjugacy. I don't know. I mean, I like to call it conjugate class. Okay, or maybe conjugacy class. Okay, and the second is that we need to prove so-called rows orthogonality. So in the previous we have proved this, right? So this is called the Cardan orthogonality for this delta ij for these two different character of the representation. Irreducible representation, which is defined to be this, which is sum over G, which is Cardan orthogonality instead is sum over the character. Yeah, and I think once we prove this, then all the word representation, the foundation is already fixed. And the next we can talk about examples and or otherwise we just go into more abstract, talk about how to view a group representation called tensor products and symmetry fusion category or other interesting thing. Okay, but for theory part, I think this is the final important one. Okay. So let's define a class function. Okay, so the function is called class function from F to G. If F is from a group G to any complex number, it's called class function. Don't worry, this is simple, right? If F, G, H, G inverse is called F of H. Okay, so basically this is called class because F is the same at conjugate class, right? So which means that if H and G are conjugate, means that H is alpha G alpha inverse, then F of H is F of G by definition. Okay, so this is the class function. Okay, so obviously that if you have two class function, their addition is class function, right? If you take any complex number which act on F is also class function. So which make the class function as a vector space. Okay, so let's see. But we can ask what is the basis? What is the basis, or at least one can ask what is the dimension of the class function? Okay, and this is simple, right? Because we know that let's say let's denote the notation that that's R, that R to be the number of conjugacy class. So R is a number of conjugate class. Okay. So R is the number of conjugate. R is the number of conjugate class. Right? For example, in the abelian group, then every group element is conjugate itself, right? So in our abelian case, that R just the number of the group element. Okay, so there are to be number of conjugate C class, right? So obviously that let's say I label this is the conjugacy class, conjugacy class 2, conjugate 3 up to conjugacy R. Right, and I can easily see that if I define let's say I define a small f, let's say called fi, which on the gj. So gj is the conjugacy j, and fi is just from 1 to R. There's a label which is delta ij. So this fi is only non-zero when act on this fi only non-zero when it act on the I conjugacy class. Okay, so obviously, obviously what this fi, right, forms the basis of class function. Okay, so means that yeah, so this is obviously right. So suppose your class function which act on the conjugacy one is called C1. Then I can just write f is C1 F1, right? Because F1 only act on conjugacy one is non-zero, right? There's C2 F2 of CR FR, right? And then your F act on conjugacy J class will just be Sj, right? And obviously they are independent, right? Because they only act on non-zero on its own. Okay, so which just directly prove, so just prove this stupid things that the dimension of the class function. Let me denote the class function, all the class function called is C lowercase g. This is not standard notation. I just for my convenience. So dimension of CG just R. Okay. Yeah. So okay, but notice the character, the irreducible character, right? So remember that the irreducible character xi, which I now is labeled the character, right, is also a class function by definition, right? Because xi act on the any group G will be trace of the irreducible representation. So all the characters we just mentioned in the previous videos are class function. Okay, so how many of them? The question is that we don't know, right? We don't know. Since we have not proven anything, we don't know how many irreducible representation it has, right? But we know that it's also orthogonal, right? It's also orthogonal with respect to inner products. Okay, so let me just quickly define that. So given two class function, one can just define inner products. Let's say fg defined to be 1 over g summation g belongs to g f of g. G. Oh shit, this should be h. Sorry, I use phi and sine phi. Sorry, bad notation. Let me just sorry. Yeah, somehow like this. Sometimes the notation is a little bit tricky. So psi of g, phi of g, and you can take the complex conjugate from the first one second. Maybe I know I did denote this second. Yeah, if you use the first one, then everything's the same. Okay. Okay, so now yeah, no, so now we don't we can keep going. Okay. Okay, so we don't know how many of them, right? But since that we know that the independent set is at most R, right? And these are what? These are linear. They are orthogonal, right? So this SI must be linear independent. So which you tell you that the number of the irreducible representation I denoted G hat is at most R, right? Because they are linear independent, because the dimensions are and the number of linear independent functions should less or equal to R. Okay, so the theorem actually, the non-trivial part is actually prove that this is exactly R. So this is what I'm gonna to prove. Okay, so theorem. Okay, so theorem says that says what? Says that if you have a the irreducible, all the irreducible representation of a character. So the irrep of the character of irrep, the characters, I should say all the characters of irrep forms orthonormal. So this is the meat of the theorem. Forms an orthonormal basis for a class function. Because obviously that they're already orthonormal, right? Because we already proved. So the non-trivial part is these words, right? Basis. So our goal is to show that. So our goal is to show that if if there is a class function, let's say alpha, right, from G to C, such that if alpha is also normal, alpha is perpendicular to all irreducible representations. Let's say alpha inner product with this SI are all 0 for all I belongs to G hat, then alpha is 0. Right. Well, once we have this, then we can conclude that this all guys things is all and span with the class function. Okay, so let me just give the corollary, right? So once we have this, then we have shown that since it forms also normal basis, right? So we prove that the number of G hat is the same as R. So this is our meat. Okay. So before we do that, let me just quickly mention some property of characters. So quickly just mention. I think this is not important, right? Property of the characters contains, let's say, I only need these 3. I think these 3 are trivial, so you can check by yourself. The first is that if you have 2 representation, you take the direct sum, then it becomes the sum of it. Okay. So this is trivial because if you take the direct sum, it's just a block diagonal form, right? So if you take a trace, just a trace sum of these 2. And then you ask about tensor, which is also their products, right? This is also simple because the trace A and tensor B, or you trace A, trace B, also linear algebra. Okay, what about if you do the so-called dual, right? You can talk the vector space dual, which is another representation. And by the way, I just want to mention that if V is irreducible, if only V dual is irreducible. And this is also simple, right? If V is irreducible, but V dual is not irreducible, then V dual can have decomposition. But if you dual it back, then you get another, right? So obviously that V dual should be also irreducible if V is irreducible. Yeah, this is a little bit, you need to check that if you use X V dual, then it becomes XV conjugate. Okay. Yeah, so only this one is a little bit non-trivial, but I mean, it's boring. So I don't want to prove. Okay, so let's go to the proof. Okay. Also, our goal is suppose that we have some class function, and we need for any representation, let's say rho and v, and one can define a called phi alpha, which is defined to be alpha of g, rho g, right? So this is from v to v. Okay, so rho g is just an automorphism of the vectors matrix, right? Automorphism from v to v. So you just take some alpha g's complex number and take all the g. Okay, so yeah, so the only I want to show that this phi alpha is actually a G linear map. So phi alpha is a G linear map. Okay, so this should be like an exercise because it's just cumbersome calculation. But let me just do it for you. So in order to prove it's G linear map, we need to show that phi alpha rho h is the same as rho h phi alpha, right? For any h. So let's say phi alpha rho h on some vector v. So by definition, which is a g alpha g rho g. So rho g and gh can be combined by the homomorphism of this rho. Okay, so let's do some trick and change g to be h inverse. Okay, so let's say h inverse. So h inverse. It's just some change in notation. You just change a variable such that your rho become. So you change g to be h inverse, right? So g map to h inverse. So gh become what? Gh become hg, right? Gh become hg. Right. So it is hgv, right? Okay. So we can pull out this rho h. Right? Become this, and the remember this alpha is a class function, right? So this guy is the same as alpha of g, so which is just rho h by alpha. Okay. So yeah. So from here. Okay. Okay, so phi alpha is a linear map, right? Okay, so suppose now suppose I can choose. So now I choose. So now I choose rho to be irreducible, right? To be irreducible. Irreducible. Then let's make so by Shor's lemma, right? By Shor's lemma, your this phi alpha will be lambda times some identity, right? So phi alpha will be lambda times some identity. Okay, and obviously there's identity. You can take a trace, right? So lambda is just 1 over the dimension of this v. Suppose this is v, and the trace of phi alpha, right? So trace of phi alpha is just what? By definition, a character, right? So 1 over dimension character. Okay, so let's say this is Carol row. Okay, or sometimes I use v, right? But interchangeably. Okay. Okay, so okay, but okay, so right. Yeah, so this is the in general, right? This is the for some particular reducible representation. Okay. Okay, so our assumption is what? Our assumption is that suppose you get alpha xi, which is 0, right? So which makes yeah, this is our condition, right? So this is just up to now. Okay, so now this is okay. So up to now, let's say suppose we for general, so this is for reducible one, right? For general one, we know that v is the direct sum of vi, right? For some I, for each one is also each one is a irreducible one, right? So there is a decomposition, right? So we can construct the phi alpha I, right, from for particular reducible representation. So yeah, and then we have phi alpha, right? So now phi alpha is for general representation B. So so our lambda is still 1 over dimension V, right? So now V is a trace of phi alpha, right? So now this is 1 over dimension V, where is alpha of G, right? By definition, alpha of G and the rho of G, right? So sum of trace of rho of G. Right, but now okay. But now this trace rho of G, right? For general rho is decomposed by a small irreducible representation, right? So this guy is just you can take 1 over G and the dimension of V, and view this as X and the less small representation I. Take the this is just take dual, and then take the complex conjugate, right? By definition, this is the inner product of the. So remember that the inner product of two class functions defined to be psi and phi. Okay, what the hell is going on? Psi and phi. Okay, so this is alpha and the psi I star, right? Because this is psi. This can decompose as psi, so there's sum of I, right? So this is sum of I G, right? So you should take the dual because with dual there's another complex conjugate which cancel with this. Okay, but my assumption is that alpha will vanish, right? Alpha will perpendicular orthogonal to all the irreducible representation, right? So this guy is 0 by our assumption. Okay, so which prove that which just show that phi alpha is 0 for any representation V, right? Because since it's irreducible since it's orthogonal to all the small irreducible one, right? So if you are bypass all the irreducible one, then sure you should bypass all the representation. Okay. Okay, so now we need to show what? So our final goal is to show what? We need to prove that identity is 0, right? So we hope to show this. Our goal is to prove that alpha G is 0, right? So right, this is our goal, right? By definition, our goal is to prove alpha is identity 0. Okay, so let's working on some particular representation. Let's say regular representation. Okay, right? So we get 0 x on phi alpha, right? Phi alpha is 0, so x on anything is 0. So let's say you work on identity vector, identity. So remember that in the regular representation, the vector space is spanned as the group element, right? Spanned as G, basically is G belongs to G. Right, so each group element view as a basis. So you get 0 is phi alpha E, right? By definition, which is a sum over alpha and the G, which rho G, let's rho G econ 1. So it's alpha G rho G econ 1, right? Sum over rho G belongs to. Okay. Okay, so sorry, it's identity, right? So how about rho G econ identity, right? So by definition, rho G econ identity should look like permutes of identity, right? But this is regular, so actually this guy is just G. But by definition, this V is span of G, right? So now you get 0 is a span of G, which show that alpha of G is 0 for all G. Okay, so the proof is done. Yeah, so the proof is done. So we just show what? We just show let me see what's going on. Okay. Okay, so we just show the character. So we just show the dimension. Originally dimension is R, right? But we just show that the number, the irreducible. So we just show that this is spanned by the number of all the irrep, right? All the irrep. And we also show that since we have the row orthogonality, so we show that all irrep are linearly dependent, right? So both are the basis. So their number will be the same, right? So we prove that the number of the irrep for a finite group G is the same as the number of conjugacy class. Nice. So this is the results. Okay. So final one is we want to prove that the column orthogonality. So column orthogonality. Okay, so let me just write down the column orthogonality and we do the proof. So after we know that the number of it is the same as the number of the character is the same as the irreducible representation, then it should be easy. Okay. Okay, so the column identity should be viewed like this, right? So you take any group element, let's say chi G and H. You get a G and you take a G and H. G and H. Let's say chi IG. Chi G and chi J H. Okay. Sorry. Yeah, it should be I. Sorry. And such I is chosen to be all the irreducible representation. And you take maybe you take conjugacy on this, right? And this guy will equals to the number of G divided by C. Okay. So what do you mean by C, right? So C is the number of conjugacy class for let me just write down. So if G is conjugacy as H, then it becomes G divided by C, where C is the number of conjugates. So C is just number of the CG. Basically, it's all the number of the group element conjugacy with G. Otherwise means that if G and H are not conjugate, it becomes 0. Okay, so yeah, this is the orthogonality that we managed to prove. I'm stupid. Okay. So this is called the row orthogonality. So let me just take some words. So in the column we talk about the group G, right? So let me just remind. So in the column that we talk about the group G, right? So we sum over the group G. So that means the same element, the same is in the parentheses, right? But now the same is in the indices. So somehow like one is sum over G, one is sum over I, sum over the irreducible rep. Okay, so let's quickly do the proof and then finish this video. Yeah, this proof is easy, right? So let's take the row orthogonality. And the original row of orthogonality is G belongs to G, Xi, G, Xj, G. So remember that the complex conjugate take on this part, or that part is actually the same, right? But it was 1 over G, right? Delta Ij, right? But now I can take I know the class function is defined on the, I know the class function is defined on the class, right? So I can take this to be, G belongs to G, and this is become the number of class, right? So I from 1 to R, which is the number of class, let's say CG, and chi I of G, chi J of G, right? So I just change the to be the number of the conjugacy class. Right, this is delta Ij. Okay, so let me just change the notation, little bit to make you guys easy say what I'm saying. So let's try it as this way. So let's say I from 1 to, okay, so very bad notation. You should change your let's change your notation from B. Okay, so let's say maybe change to K. Okay, K from 1 to B. So B now the B is a number of the, let's say B is a number of the conjugacy class. Okay, so sorry about the notation confusing. And I know denoted this guy is called CK. CK is the number of the class, number of the conjugacy class corresponding to CK, corresponding to K, and the G, and let's say X. So this is XICK, right? So CK is element, SJCK bar. This delta Ij. Okay. Very difficult. Okay, so let's write T as a matrix. Basically, it's chi I Cj, right? So once I label the conjugacy, the number of conjugacy by J, and then I label the number of different irreducible class by I. And then we already proved they are the same, right? So in this case, that T is a square matrices. So T is a B by B matrices, right? We already proved in the previous. So one can write this equation, right, as a matrix. Looks like T. Let's say C1 divided by G, the C2 divided by G, that's up to C B divided by G. But there are, and these are diagonal matrix, and then the T transpose and complex conjugate, right? Remember T is a unitary transpose and complex conjugates, which is identity matrix. Okay, and there are B identity matrix of B. Okay. Okay, so let's write this matrix called D. Okay, so we get T dt transpose T, which is identity. Okay, so easy to change this to be T inverse is dt transpose, right? Okay, so yeah, and the massage this, right? You get the T inverse, you get the you let's see. Yeah, let's say you times T. Okay, so you times T from the right side, you get the let's see. Okay, so let's times T on the right side, and the times D inverse to the left hand side. So D inverse. So this is identity, right? So you could become this. Okay, so this is amazing that some guy can get this. Okay, so T bar T is D inverse, right? So remember the D inverse is just what? It's just G divided by C1, right? So G divided by C1, G divided by C2, up to G divided by so-called CB. Okay, so 0, 0. Okay, so now everything's clear, right? Because you just take the so just see the main, so see the entry, right? So these guys just, Yeah, there's a two matrices, right? This element is just these two times these two, right? And then you write down, you remember this T as a character, right? So you just working on this row times this column, and then this row times this column, and you can immediately get the results. Okay, so theorem, we just prove it. Basically, it's xi, let's say g, and xi h complex conjugate where here or there is the same. All the character I belongs to G. Basically, or I from 1 to B is basically if G and H are conjugate, then become G divided by, let's see, G. Otherwise, otherwise is 0. This guy is called what? Centralizer, right? So this is the centralizer. Okay, so this is the proof. Okay, so let me just show you guys. This is exactly the same as the online, right? If you go to online, this is called the centralizer. Okay, and then we just prove it. Okay, so very happy. Okay, so let me just final remark. So let me just write down the conclusion. So conclusion is that in a finite group, every representation is a direct sum of the so-called irreducible one. And each irreducible one have associated one character. And we have proved that the character, if character is the same, that means the irreducible representation is the same. Okay, so all the problem of the complicated finite group representations finally become some class function called character. And this character has two properties. One is the row orthogonality, also called the short orthogonality. Okay, and also the column orthogonality, which I spent like 1 hour for 30 minutes for this, 40 minutes for this, just to prove it. Short orthogonality. And why this is called shorts, because everything comes from the shorts lemma of the irreducible representation. Okay, so the example we will look in the other videos is basically using 1 and 2 to compute the character and find out all the irreducible representation for some small group. Okay, so that's it. And in the future, after we finish the examples, I will talk about the tensor product and the factorization. And I will basically, so actually my final goal is to show that actually one can define a so-called representation G. Rep G is a representation group category, such that each object is basically the group rep, and the morphism should be what? G linear map, right? So G linear map. And I want to show that there is a simple object which is called irreducible one, and the morphism are basically only a complex number, and then they have the tensor and the fusion. So basically, our conclusion, I will try to establish the results that representation of G is actually so-called symmetric fusion category, which is many in the condensed matter theory or other like the algebraic geometry important object called symmetry fusion category, which is the simplest version of the thing called the unitary modular tensor category. So symmetry fusion category is a special case of unitary modular tensor category with the trivial braiding. Okay, so this is my final goal, just to using the larger perspective, so-called symmetry fusion category to understand the whole group representation for finite group. See you guys next videos.